Yeah. So, hi all. A very good evening, and welcome back to the sixth week of the TA live sessions for uh, artificial intelligence, knowledge representation, and reasoning. And yeah, so this week we'll be discussing some questions related to week 7 content, which continues with the discussion of prologue from week 6, and then we go into rule-based expert systems and readiness. So, without further ado, let's get started with the questions. And also, I do remember that there were a few doubts raised towards the end in the previous live session. I will be covering them towards the end of this session. Okay, but first, let's discuss the questions from week 7. All right, so by the way, can you hear me clearly and is my screen visible?
Yes, sir. You are clear and your screen is visible.
Okay, thanks, Mohan. So this is the first question in front of you. So you are told that consider the following clauses that includes the negated goal. Okay, so C3 is basically the negated goal. Okay, and the first two clauses are C1 and C2, and we are given two types of proofs, proof 1 and proof 2. Okay, And what you have to say is which of the following options are true. Does proof 1 use SLD resolution, or does proof 2 use SLD resolution, or do both of them or neither of them use SLD resolution? So I'll give you a moment to think about it while I'll also create a poll, and then you can share your thoughts over there. Hi Chitranjan, am I audible now? Can you hear me? Hi Vipul, good evening. Good evening to all the new joinees. Uh, Others, is my audio okay? Am I audible? Just can you just confirm once? Just yes or no, you can type in the chat. Okay, okay. Thanks, Kishore. So, Chitranjan, I hope the issue is resolved. Otherwise, there might be some issue at your end. Maybe try rejoining and hopefully it will be fine. All right. So, yeah, to the new joinees, this is the first question that we were about to discuss. I've also created a poll. You can go through the question and share your thoughts over there. Okay, we already have a couple of votes. Okay, nice. So there's one vote for option A. It says that both proofs use SLD resolution, and one vote for option C, which says that only proof 2 uses SLD resolution, but proof 1 does not. Alright, so if you remember the lecture slides, one of the important or one of the first points or key points regarding SLD proof or SLD derivation was that the first resolvent has one parent from the goal and one from the program. Okay, so with this in mind, let's see our options. Let's see the two proofs that we had. Okay. I would also request you to mute. Yeah, thanks. If you don't have a question, that will help. Thanks. Okay, yeah. So let's look at the two proofs. So the first proof, uh, the first resolvent is QA coming from clause 1 and clause 2 with the substitution of replacing X with A. Okay, so this is basically not P or Q, which is P implies Q, and using P implies Q and PA, we are deducing QA. Okay, and then using QA and not QA, we are getting a empty thing from R1 and C3. Okay, but if you observe, this proof 1 does not use so if you go back to the definition of SLD derivation, the first resolvent has one parent from the goal and one from the program. This is not happening in the first proof, right? Because it's only using the first two clauses and it's not using the goal, which is C3, the negated goal. So although both proofs are correct, proof 2 is the one that is using SLD resolution and proof 1 is not, right? Because in proof 1, the first resolvent is coming from C1, the first clause, and C3, which is the negated goal. Okay, so the correct answer would be that proof 2 uses SLD resolution, but proof 1 does not. Alright, so this is a pretty straightforward question right from the lecture, so I hope there is no doubt about it. Uh, is there any doubt? That's great. If there is, just let me know. In the meantime, let's move on to the next question. Okay, so this is the second question in front of you. So P is a atomic formula in first order logic. Then negation by failure, which is represented by a slash followed by a plus sign, and then the P, which is atomic formula. So what does that mean in prologue? Which of the options do you think would be correct in the case of negation by failure? So once again, I'll let you go through the options and I'll create a poll in the meantime. Alright, so I have created the poll and you can share your thoughts over there, or you can also write in the chat. So remember, negation by failure is uh, like not, but not exactly not. Okay. Okay. So we have one vote for option C and D. What about the others? Do you agree with this answer? Okay. We have another vote for option C and D. So okay, and another vote in the chat by Orkodeep. So yeah, as it turns out, C and D are in fact the correct options because negation by failure will return true when all the attempts to prove P fail, and it will return false when at least one attempt to prove P succeeds. Okay, this is also pretty much a recall based question, and if this is not clear to anyone, the next question also deals with negation by failure, and hopefully when we discuss the next question, the concept will become more clear. Okay, so remember these options and let's move on to the third question so that any query you might have regarding negation by failure might be clarified through that. Alright, so here's the third question. So you're given a prologue program, okay? So basically link xy defines that there exists a direct link between uh, x and y, and root xy defines that there exists a path that so a path consists of one or more links from x to y. Okay, so the program is defined in this way. So there exists a route from x to y if there is a link from x to y. This is one definition. So if x and y are directly connected, then there is a route between them. Or there's a route between x and z if there is a link between x and some intermediary node y, and a route from this intermediary node y to the end node z. Okay, so this is a definition. And then you are given that there's a link between A and B, there's a link between A and C, and there's a link between B and any other variable y if there's a negation by failure of link A to y. Okay, and the question asks you select the queries that return a true or return one or more solutions. Okay, so I'll first let you go through the options and then we'll shift to prologue to see what are the possible answers and what is the reasoning behind the possible answers. So I'm not creating a poll for this one. I'll just give you some time to go through the options and think about them. All right, so let's look at the options one by one. So the first option, option A. So how many of you think that this will return a true or more than one solutions when you query link a comma variable y? What will be the expected output in Prolog? Will it be true? Will it be false? Or will it be a bunch of solutions? More than one solution. Yeah, that's right, Somil. Thanks for the answer. Uh, this is true, in fact. So when you query link a comma y, there will be two answers possible, which is B and C, because you already have from the knowledge base that there is a link between A and B, and there is a link between A and C, right? So Prolog will produce two outputs for this case. So link a comma y, the first option is the correct option because it satisfies the conditions that the question asks for. Okay. What about link a comma e, the second option? False, right? That will be false because uh, we don't have any such fact regarding a link between a and some e node, right? So it will turn out to be false. That is correct. So link a comma e, option B is not correct. What about the third option? Is there a route from a to y? True, right, right, right. So thanks, Somil and Mohan. Uh, yeah, there will be a route from a to some variable y. So just because so using the same reasoning that we used in option A, so there is a link between A and B and the link between A and C, right? And if there is a link between two variables, we can say that that also forms a root. So just by that logic, we can say that there exists two routes from A to B and A to C, right? So option C will also return true or more than one option or more than one solution, right? So option C is also correct. Now what about option D? What do you think? True. Okay. Okay, so we have a couple of answers. Some answers say that it will be true, some answers say that it will be false. All right. Okay, so I think the votes are shifting in favor of false now. Okay, let's do one thing. Let's open Prolog and let's have a look at the program. Okay, let me just shift to my whole screen mode. All right, I hope my screen is visible. So I already have this program written, so I'll just consult it.
Can you make the fonts a bit bigger?
Uh, I'm afraid that's not possible, Mohan, because uh, I'm using the default screen.
Okay.
But yeah, maybe you can try zooming in. Uh,
Okay.
yeah, or let me try if that works. Uh, yeah, I don't think it works in my case, but yeah, sorry about that. But anyway, I hope it's still legible to people who are viewing it. So let's query root a comma e. Okay, and it does turn out to be true. And don't confuse this false for an answer. This just says that there's no other answer other than true. Okay. So why did it happen this way? Let's trace the program and then figure out why this happened. Okay. So we queried root a comma e. Okay. So this program first called root a comma e. Right? And as per the definition of root a comma e that we had, it will first check whether there is a link between root a comma e, right? Because that was the first thing that our definition was stating, that there is a root between x comma y if there is a link between x comma y, right? So let's see, it will check whether there is a link between a comma e. It will fail because we know that there is no link between a comma e as per our knowledge base, right? So it will go back to the other definition of root a comma e that we had, which is this. There's a root between x to z if there's a link between x and some intermediary node y, intermediary variable, and a root from this intermediary variable to z. Okay, so it is redoing root a comma e, and it is checking whether there is a link between a and some variable that is denoted by this alphanumeric over here. Okay, it finds out there is a link between a and b as per our knowledge base, right? Now it will check whether there is a node between, there's a root between this intermediary variable which has been assigned b for now and e. Okay, so remember that there is a different definition for a link between b and some variable y, right? So there's a link between b and a variable y if there is a negation by failure link a comma y. So let's see what happens. It calls, so when we go to check for whether there is a link between b and e, it first checks whether there is a link between a and e, right? There is a fail. Okay, so it redoes e comma link, redoes the checking of whether there is a link between e comma e, and ultimately it returns true. So can you relate this to the second question that we discussed? So negation by failure returns true when all attempts to prove b fail, right? Here all attempts to prove that there is a link between a comma e failed, so it returned true, and that's why the end result, the end output here was true. Okay, so any doubts about this one?
Sir, can you repeat once why it came true again after all the queries,
Sure.
after the failure of all the options?
See, so we start with root A, checking whether there's a root between A and E, right? And to do that, we first go to the definition of root that we had put in, right? Which is there's a root between x and y if there is a link between x and y, right? So it will check whether there is a link between A and E. So it checks whether there is a link between A and E, right? And it fails because there is no link between A and E, right? So this top definition of root failed to give us a result. It will go to the next definition of root by default, right? This says that there is a link between x and z. So here x is A and z is E. Okay. There is a link between x and z if there is a link between x, which is A, and some variable y, and there is a root between y to z, which is E. So let's see what the prologue says. So it again checks whether there is a root between A comma E, and to check that it first sees whether there is a link between A and some variable that is denoted by this underscore 23382. Okay, this is just a variable identifier, and it finds out that there is a link between A and B as per our knowledge base. So so it assigns this variable the value B for now. Okay, and then it continues to the rest of the definition to check whether there is a further route from B to E. Okay, because that was the second part of the definition of a root, this part. Okay, is it clear until this point?
Yes, sir. Yes, sir.
Okay, now to check whether there is a root between B and E, we again go to the definition of a root, right? So the first line of the definition of root says that there is a root between x and y if there is a link between x and y, right? In this case, x is B and y is E. So it will check whether there is a link between B and E. That is exactly what it is doing, right? Now, to check whether there is a link between B and E, it goes to, sorry about that, it goes to this definition which says that there is a link between B and Y if there is a negation by failure of a link between A and Y. What this basically means is that if A is connected to something, then B can't be connected to it. Okay, let's go back. So it checks in order to check that there is whether there is a link between B and E, it checks whether there is a link between A and E. Okay, now we know that this will return a failure because as per our knowledge base, there is no link between A and E, right? So all attempts to prove this link between A and D have failed, and hence the negation by failure will force it to return true, right? So when you redo link B comma E, it will turn out to be true. Since this turns out to be true, this turns out to be true, root B comma I turns out to be true. Finally, root A comma I also turns out to be true. Okay, so is it clear
Okay,
now?
sir. Got it. Got it. Got it.
Yeah.
Yes, sir. Yes.
All right. So we saw till option D. So till now we have options A, C, and D as correct options. What about option E? Let's check. Okay. This checks whether there is a link between B and some variable Y. Okay. So this will again go back to the definition of link between B and Y, which is this, right? So in order to check whether there is a link between B and some variable Y, it will check first whether there is a link between A and some variable Y. That is what it is doing over here. It is checking whether there is a link between A and the same variable, right? And we know that there is a link between A and something from as per our knowledge base, right? So it will get link between A and B, right? Now, if you remember from question 2, it will return false when at least one attempt to prove P succeeds, right? Here we have one attempt to prove P as a success. This is P basically, whether there is a link between A and some variable, and we have at least one attempt to prove P that has succeeded. So it will return false, right? And hence the end result will be false. Do you agree with me? Okay, I hope that is clear. And then the last option is just something we saw as a subroutine while discussing option D itself. We saw that link B comma E turned out to be true, right? And it will turn out to be true. Let's just verify it. It did turn out to be true, right? So our correct options in this case would be link A comma Y will turn out to be, will give either a true or one or more solutions C, D, and E. Okay. So I have these results uh, written over here. I'll just let you go through it, and we have already used trace to see what happens and what doesn't happen. And then we'll move on to the next question, or if there are any doubts, we can discuss the same. Let me just shift back to my normal presenting behavior. All right. So I'll just let you go through the solution once, and I can zoom this though. I think so. Yeah. If there are any doubts, do let me know. All right. So I guess there are no doubts. That's great. Uh, let's then move on to the next question, which is question 4. So this is about red cuts and green cuts. Okay. So if you remember from the lectures, we saw that uh, there are two kinds of cuts. One that uh, alters the meaning of the program, and one that doesn't alter the meaning of the program. And the one that changes the meaning of the program, if we remove that cut, that is a red cut, and the other one is a green cut. So that was just a refresher for anyone who might be a bit foggy on it. And let's see the question. So we are given two versions of a remove all predicate as per the definition over here. Okay, so we have remove all 1 and remove all 2. So what this remove all basically does is you give it a list as an input and value e, right? And what it will do is it will give you as output the list with all the instances of that particular value e removed from the list. So if you give it a list like 1, 2, 3, and you give a value of e as 2, it will return you a list 1 comma 3, basically with the value 2 being removed from there. Okay, so that is what the purpose of this remove all predicate over here is, and there are two definitions of that with using two different forms of cuts, and you have to identify which one is a red cut and which one is a green cut. Okay, so remember the definition or the logic behind a red cut and a green cut. So what you can do is, I'll give you a hint. Try thinking about these definitions with the cut removed and think about what the output will be, and then decide whether inclusion of the cut is having any effect or not from the case where we are excluding the cut. And from there you can decide which one is a red cut and which one is a green cut. Okay, so I'll let you think for a while and I'll create a poll in the meanwhile. Right, so I have created the poll. Okay, I guess I was on mute. Yeah, so I was saying I've created the poll and you can share your answers over there, or you can just write it out in the chat. You can also feel free to speak up if you want to. Okay, so we have one vote for options A and D, which says that Mohan, may I request you
You know,
to
watching.
please mute yourself if there is no question. Okay, I'll mute you. If there's any question, feel free to unmute yourself. All right. So, okay, so we have one vote for option A and D, which says that remove all one contains a red cut and remove all two contains a green cut. And then we have one vote for options B and C, which says that remove all one contains a green cut and remove all two contains red cuts. Right. So there are like these are conflicting opinions. So let's see. Okay, so we have one more vote in favor of options A and D. Okay, let's just quickly revise the definition of a cut. Okay, so basically you have something over here, if something else over here, then a cut, then something else over here, right? What this basically means is that if this part evaluates to be true, what this cut is going to do is it will let the control or transfer, let the flow go on to the next part, which is this part, right? And it will restrict the evaluation of this thing to this remaining part, right? Because this part has already turned out to be true. If on the other hand this thing turns out to be false, what this cut will do is it will not let the flow go to this part at all. It will just go back from here itself and it will look for the next definition. Okay, so now let's look at the options. So here what the first remove all definition says is that, so when you give in an empty list, it will output an empty list. That makes sense. Next line is, so if you have the list in the form of a head and a tail, right? If E is equal to H, okay, so if E is equal to the first element of the list, then you let uh, this cut lets the flow go to this part, right? And it restricts the evaluation to this part, okay? So once E is equal to H, we will remove H from the list and then we will explore whether explore the remove all predicate recursively on the tail part of the list, okay? And if E is not equal to the H or the first element of the list, we won't even go into checking whether this part is true. If this is false, we will straight away go to this definition, okay? Which basically says that it basically means that E is not equal to H, okay? And what this will do is it will remove H and not remove H, it will add H to the output list as well, which is what is being done over here. And then it will explore the rest of the list, which is the tail of the list. What removal 2 does is that if E is equal to H, the same thing, right? But the difference over here is in the definition of this, the third definition of removal 2, right? Here it is once again checking whether E is not equal to H, right? So essentially this cut can be removed and the meaning of the program will still remain the same, okay? So in order to verify this, what I have done is I have created two versions of these remove all predicates, okay? One one is the removal predicate as it is, okay, with this cut. Another version is the removal predicate without this cut, okay, and I call that removal 3. And I've created another version of this one as well, call it removal 4 with these cuts removed, okay. So let me just show it to you, just give me a moment. All right, there you go. So I hope you are able to see this file over here. So these first two definitions are the ones that are given to us, okay, and this removal 3 and removal 4 are just the same two definitions, removal 1 and 2 respectively, with the cuts removed, okay. So if you see here we have no cut, here we have a cut, And similarly here we have two cuts and here we do not have any cuts. Okay, and let's try and see what is the output. Okay, there are some warnings, we'll ignore them. Alright, so let's check remove all 1 first. Let's say 2 is the value of E that we want to give in. Let's say our list is 1 2 3 2, and let's say 4 or 5 is also at the end. Okay, and X is our output list that we want to get, right? Okay, so what this did is it removed all the places where 2 was occurring, right? And it just returned 1 3 and 5. Let's see if there are any other solutions. There aren't, there is only one solution, right? Now let's check the definition of remove all 1 with the cut removed, okay, which is remove all 3. Let's check. Okay, it returns 135 and it returns false again, which means there is no other solution possible, right? Which basically means that, okay, let's check remove all 2 first. It returns 135 as well and nothing else. Now let's check remove all 4, which is just remove all 2 with the cuts removed. Okay, it returns 135. Okay, this is a bit strange. Ah, here is the mistake. Sorry about that. Alright, so I've corrected the mistake over here. There was a error in the definition that I had made while creating the versions of the remove alls without the cuts, and I hope it will be clear now. So let me consult it once more. Right. Okay, now let's check the options once more. So remove all 1 gave us only one answer. Remove all 2 also gave us only one answer. Now let's check remove all 3. Okay, now this is giving erroneous answers, right? After we have removed the cut, it is giving us all kinds of wrong answers. Now let's check remove all 4. This still gives us the correct answer even with the cuts removed, which basically means that the presence of the cut or the removal of the cut is not having any effect on the definition of remove all 2, which means that the cut in remove all 2 is a green cut, whereas when we remove the cut from remove all 1, it starts giving us different answers. It changes the meaning of the program itself, right? So the cut in remove all 1 is a red cut. Okay, I hope that was clear. Okay, that's great. Thanks for the thumbs up, Somil. I'll shift back to my regular presentation mode. Alright, yeah. So the correct answers are remove all 1 contains a red cut and remove all 2 contains green cuts. Alright, so any doubts about this particular question, or should we move on to the other parts, other questions? Okay, thanks for the message, Somil. Okay, in case there are no doubts, let's move on to the next question, which is question 5. Okay, this question tells us study the following program using Prolog again without using tabling, right? And then answer the question. Okay, so here again, link xy defines a direct link between x and y and vice versa. All right. So this is actually a pretty straightforward question if you think about it. So we are given three facts. There's a link between A and B, there's a link between A and C, and there's a link between B and C. And then there's a link between two variables y and x if there is a link between x and y. So there's kind of a cyclic way of defining this, making this definition, which is likely to make it prone to errors, right? So what the question asks is select the query that terminates after finding all answers. So which of the options do you think will be correct? Okay, so we have a couple of answers. Itachi Uchiha. I'm sorry if I'm mispronouncing it. So you say it's option C. Somil says it's option B and C, and then Mohan says it's option A. All right. So, but think about it a little bit more. All right. Let's see. So remember the definition of link y comma x is that if there's a link between y and x, if there's a link between x and y, right? So because of this cyclic nature of this definition, exactly, yeah, right, Somil. So Somil says it will go into a loop, right? So it will go into an infinite loop and it will never end, right? So let's just shift to prologue once more for this one last question regarding related to prologue. All right, let me just consult it quickly. All right. Now let's check all our options. Okay. So the first option was whether there is a link between x and y. Okay. So if you check whether there are any more answers by using a semicolon, it will give another answer. And if you keep pressing, it will keep giving you answers. Okay. It will never end until you press enter. That is if you force it to stop. Okay. So it is going into an infinite loop. Okay. Let's check the other option. Option B, which was link a comma y. Okay. So it returned a B, it returned a C, and again it is going to continue doing that in an infinite loop, right? Until you force it to stop. Let's check the third option, which is link a comma b. It returned a true, right? Because it is a fact in our knowledge base. But if you give a semicolon, it will keep giving you true. It won't end because of the because of it going into a infinite loop, right? Because of the left recursive way of the definition, right? So even option C would not terminate, right? Similarly, the next option would also not terminate. Let's just verify it. E comma F. There's nothing, right? This is in fact giving some error itself. It's not even terminating even if you press enter, right? So there is some fault with it, with the definition itself. So the correct answer would be none of the above. Okay. So Somil says if we use tabled execution C, would C be correct? Okay. Okay, so I will encourage you to try this and then get back to me in the next live session and let's see what the result is. Okay. All right. Okay. So this is just a brief explanation. This is also a recall type question. This rule is left recursive, so it will go into an infinite loop and produce duplicate results. Okay, just a brief explanation. All right, so now we are done with the questions related to Prolog, and we are moving into the territory of rule-based expert systems. Okay, so just a heads up for those of you who might have done the other AI course offered by Professor Khemani, which is AI SMPS or Search Methods for Problem Solving. We also covered RateNet and rule-based expert systems over there. So while we are going to discuss some questions related to that today, if you want some more questions, you can always revisit the live session recordings for that particular week from AI SMPS, okay, which will also be available in the same YouTube channel in which these recordings are being uploaded. So I'm not exactly sure which week it was, but if you just go over there and check the AI SMPS videos, one of them would be having questions from RateNet. All right, so let's get to the questions over here. The sixth question asks us, in RateNet, refactoriness refers to which of the following? This is again a recall based questions directly from the lectures. So what do you think? Which of the options will be correct? Okay, anyone? Do you remember what does refactoriness refer to? So remember here the situation is that you have a set of rules that you can fire and you want to decide which rule you have to fire, right? So you that is what is basically called a conflict set, which is basically a set of rules that you could fire at a given particular point of time, right? And you have to decide which rule you should fire. And then there are some of these conditions like refactoriness that might help you decide which of these rules to fire or not fire. Okay. So by the way, are you guys like have you guys watched the videos about the rule-based expert systems? Are you familiar with the paradigm? Should I just give a brief explanation of what that actually is that we're trying to do? Okay. So we have one vote for option C. Vanshika says option C is correct. Thanks for the answer, Vanshika. But let's see if it is the correct or not the correct option. All right. So Somil says that it would be good if we had a brief. So I'll quickly just give a very brief introduction to what exactly are we trying to do. All right. So in rule-based expert systems, what you have, so you have a certain set of rules. Okay. So you have rule one. Okay, and this has a certain format. Okay, I'm not writing in the proper format, but you can check out the format from the lectures directly. There's something called ops 5 that they use. Okay, so there's a rule that looks for a certain set of conditions. If these conditions match, then it will make some changes to the database and add some other things. Okay, so this is basically called a working memory. Okay, so we have something called a working memory which has certain set of facts, right? And these are all the timestamps associated with those facts. So what this rule will do is it will look for patterns in this working memory. If these patterns match, then this rule will be eligible to get fired. Okay, so if I just have to represent it with a very brief diagram. Okay, so let's say these are some of the patterns in the working memory that you have, and this matches with the preconditions for some rule. Okay, so you can apply that rule, get some new conditions, and you can add it back to the working memory, right? Now the issue over here is it may happen that at a time multiple of these rules could be candidates to be fired. Okay, so basically when you say you fire a rule, you mean that you apply that rule. Okay, so it might be that you can fire rule 1, rule 2, and let's say you can't fire rule 5, but you can fire rule 7. Okay, so these rules 1, rule 2, and rule 7 will form your conflict set, and you have to select which of these rules you want to fire next. Okay, and this is something you want to resolve. So this is the very brief introduction to what exactly we're trying to do. And this question here asks about refactoriness. Okay, so uh, okay, let's just quickly have a look at the lecture notes. So there is something called conflict resolution. Okay, so this small diagram over here, I'll just zoom in a little bit. This just shows the workflow of what I just discussed. So you have a working memory, you have some rules. If you have a match, then this rule gets a part of the conflict set. You use some method to resolve the conflict set, and you select a particular rule from this conflict set, and then you fire that rule and use the data to add some new data to the working memory. Okay. Now what refactoriness does is this says that a rule instance may fire only once with a set of matching WMEs or working memory elements basically. This is particularly relevant when the selected rule does not modify the working memory elements matching its preconditions. Else, only this rule would keep firing. Okay, so this is basically a way to ensure that there's there's no one rule that always keeps getting selected to be executed and all the other rules are neglected. Okay, so to avoid that kind of situation, this refactoriness is used as a conflict resolution strategies, one of the conflict resolution strategies. Okay, this is not the default strategy that we use. So based on that, uh, now what do you think is the correct option? Okay, so Somil says it's A, but think about option B. Right. Uh, Thanks, Orkudeep. So we just saw that the purpose of refactoriness is to ensure that one rule doesn't keep on getting executed again and again, right? Right, that's right, Vanshika. So option B would be the correct answer, which is that refactoriness refers to blocking of the same rule data pair from getting fired again and again. Okay. So this is just one of the possible ways of conflict resolution. There are other ways like specificity or recency, some of which we may have a look at in the following questions. Uh, for the other parts, if you haven't yet watched the videos, you still have time. You can just go through them. It's a pretty straightforward concept and one of the most easy scoring parts of the course, right? This written it part. So I would encourage you to uh, score as much as you can in these particular questions. All right. So this was just a definition based question. I hope there is no doubt about this. Let's move on to the next question. So okay. So I remember I was talking about something called OPS5 or OPS5. This is the one question related to that. So basically, when you specify a production rule, you do it in the format of this OPS5 like language. Okay. So a production rule in OPS5 like language is given over here. So this is the rule. I'll just explain what this rule is. It's given along with a working memory. So this is your working memory containing only one element. Okay. And the timestamps are represented by the sequence number. Okay, so this is the timestamp of this particular element. Okay, one is the timestamp of this element. Now allow the production system to fire all the rules and come to a halt. Okay, so it will come to a halt when no further rule can be fired. Okay, here we have only one rule. Okay, so the structure of this rule is something like this. You start with a parenthesis. Okay, so this is called P. Okay, so P is the identifier. Fun rule is the name of the rule. Okay, this part is the precondition that it will check, or it will try the pattern that it will try to match from the working memory. Okay. Okay. So this is another something called row. Num is a variable. Okay. So anything or an attribute, not a variable, an attribute. Anything that is preceded by this upward arrow kind of thing, that is an attribute. Let me actually just revisit the lectures to explain it better. Right. So here it is. So this is an example of some other working memory elements. So these numbers are basically the timestamps. Okay. These are the class names. Okay. So total marks is the class. Next is the class. This array is a class. Okay. These are attributes. Anything that's preceded by this upward arrow kind of thing is an attribute. So student is an attribute. Rank is an attribute. Index is an attribute. And then you have values. Okay. So one is a value for rank. Sangeeta is a value for student, 97 is a value for marks, right? So on and so forth. Similarly, here row is the class name, num is the attribute, a is the value or a variable you could say, sum is another attribute, and this is another condition that you have to check. Okay. So basically what this rule says is if you have something like this row num a, so you have some number a num and you have the sum, which is if the sum is less than 10, then you add this particular thing to the working memory. Okay, so make means that you add this to the working memory. So let's actually take an example and see. So what this fun rule will do is it will look into the working memory and it has only one element, right? So it will take that element and it will see that this is matching, right? Because we have num as 1 over here, and that's fine, and you have sum as 1 and 1 is less than 10. Okay, so this pattern is matching. So what this rule will do is it will make a new element and it will add this to the working memory. So after this we will have something like 2. 2 will be the timestamp of this new element that is being added, and that will be row num. So num will have now a value b, which was initially the value of sum. Okay, so this will be row num 2, and the sum will be replaced by the sum of the values a and b. Okay, so here the values of a and b were 1 and 1, so the new element would be 2 dot row num 1 sum 2. Okay, so is it clear until this point? Any doubts about until this point the discussion that we had? All right, so thanks for the thumbs up, Somil. So based on that, I want you to continue firing these rules or executing these rules until we can fire no more rules. Okay, which will basically happen when the sum becomes greater than or equal to 10. And then you have to tell me how many times exactly this rule was fired. Okay, so we have a couple of answers. So Sumati says that it will be fired 5 times. Vanshika says, and Itachi says that it will be fired 4 times. Okay, so let's look at the execution steps and then let's see how many times it is going to get fired. All right, so this was the initial position, right? The first element of the working memory. So here the condition is satisfied. So we fire fun rule and we add the new rule, the new element to the working memory, right? Which is num1 and sum2, which is basically 2 is coming from this 1 plus 1, right? This also satisfies the condition. Okay, so we'll once again fire fun rule and we'll add this new element. Okay, so this 2 will go over here and this 3 will correspond to 1 plus 2. Again the condition is satisfied, so we again fire fun rule. This 3 will come here and this 5 basically means this 2 plus this 3, right? Okay, still the condition is satisfied, so again we fire fun rule. 5 comes here and this 8 corresponds to this 3 plus this 5. Still this condition is satisfied because the sum is still less than 10. Okay, so we once again fire fun rule. 8 comes here and this 13 becomes, so this sum becomes 5 plus 8, which is 13. Now the sum has become greater than 10. Okay, so we now can't fire fun rule anymore, so no more rules to fire, right? So let's count how many times fun rule was fired. Once, twice, thrice, 4 times, 5 times, right? So fun rule was fired 5 times. So the answer will be 5. Okay, I'll just shift to the solution once more and let you just go through it, and if there are any doubts, do let me know. All right, so any doubts about this question? I hope it's clear. Okay, great. So now let's move on to the next question, which we kind of have already answered. So it's the same scenario. We just have to answer the last value of the sum attribute. Okay. So we just saw that this was 13. So that will be the answer. The last value of some attribute before we stopped firing any rules or before we halted. Okay. So that was 13. Hi Suresh Chandra. Yeah, so we are discussing questions related to week 7 content. All right. And no issues if you joined a bit late, that's fine. Uh, you can always revisit the recordings later on if you want to. All right, so this was pretty straightforward. Let's now go to the next question.
Hello, sir.
Yeah,
Sir, why is the last value of the sum 13? It's more than 10. It should have been 8. That's a bit confusing.
see,
Uh,
when the value of sum was 8, the pattern was still matching, right?
yes, yes.
So you fired fun rule once more, and whatever result you got, which is basically this, you did add to the working memory. Okay.
Okay.
Only
Oh, okay,
after
okay. So,
adding it, you saw that this pattern is not matching. So you stopped firing.
yes, 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 yes.
Yeah, that's why.
Okay, okay, sir. Okay, sir.
Yeah. All right. So the next couple of questions will be based on this RateNet that is shown over here. I'll zoom into it. Uh, just give me a moment. Yeah, I hope it's a bit bigger now. Right. So basically, you are given a RateNet, okay, that classifies vehicles, and you are also given a working memory that I'll show in a while. And the timestamps are also represented over there. So these A values are the alpha nodes and the B's are the beta nodes. Okay. So these yellow colored ones are the beta nodes and these A's, the white colored nodes are the alpha nodes, which is just a nomenclature. Uh, and now let me show you so what this rate in it basically means is that, so these beta nodes represent, you could say in a way, uh, different rules. Okay. So if you take this F1 car over here, this basically says that, so this has three arrows coming into it, right? So let's see what exactly these three arrows mean. Okay. So the first arrow, let's trace back, goes all the way to wheel over here, right? This means that one of the condition that needs to be satisfied is that the wheel has to be slick. Okay. The second arrow says that the passenger limit has to be 1. And the third arrow states that the power of the vehicle has to be greater than equals to 700 horsepower. Okay. If these three conditions match, then you can fire F1 car rule. Okay. Similarly, luxury car, regular car, and minivan cars, all these have different preconditions. Okay. This is just an example of what the rate net basically signifies. And now this is your working memory shown here on the right side. Okay. So you have, so remember in the previous question we had just one element in the working memory. Here you have 10 of them. Okay. So is the setting clear? All right, great. So now let's go to the questions. All right. So the ninth question asks us, according to regular car rule, which of the following is true about regular cars? Okay. Let me just go back to the written it and then you can have a look at it. So this is the regular car rule over here, which is B3 node, okay? And with what are the conditions basically that need to be satisfied? Can you just have a look and point it out to me? All right. So we have one answer. So Somil says that the condition that need to be satisfied are, okay, let me shift to the Jamboard actually, that will be more clear. All right. So this is the rule that we are trying to analyze, right? Regular car. And the first arrow comes from over here, which means that the wheel has to be, it has to have a regular tire, right? The second arrow states that the limit has to be, the passenger limit has to be 4, right? Like this. And then the horsepower, the power of the vehicle has to be greater than equal to 100 but less than equal to 300. Okay, so these are the preconditions that need to be satisfied. Let's go back to our question now. So we saw that the only thing that is not true about regular cars is this slick tires, right? So the correct options would be A, C, and D. I hope that was clear. Any doubts about this question? Okay, great. Now let's go on to the 10th question. Now we come to conflict set. Okay, so in the first round, which of the following will occur in the conflict set? Okay, so this is basically the rule. Okay, and these are the working memory elements that it takes in as input, basically you could say, or that it matches with. Okay, the timestamps of the elements basically. Okay, so maybe you can take a snapshot of these options and then I'll shift to the written it and the working memory elements so that you can find out the or work out the correct answer. All right, so now I'll shift to the, yeah, so here you have the written it and the working memory. Okay, so I'll remove these lines over here. And let's check which of these are true. Okay, so the first option was F1 car. Okay, and the rules and the elements that I took in were 204, 205, and 210. Okay, so let's see. So here is the F1 car rule. Okay, and it says that it takes into account 204, which basically says that the power of this particular vehicle called K32 has horsepower of 800, which is greater than equal to 700. Okay, so let's check whether that condition is satisfied. That is in fact true. Okay, so that part does match. All right, let's check 205 now. It says that the wheel is regular, right, for the same vehicle. Now F1 car preconditions require the wheel to have slick tires, right? But here the tire is regular. So this is resulting in a mismatch of the preconditions. So F1 car will not be a part of the conflict set. We can't fire F1 car based on working memory elements 204, 5 and 10. Okay, was that clear? Any doubts about that? Okay, great. Now let's check the other options. What was the other option? Luxury car, again the same elements 204, 5 and 10. Okay, so let's check. So luxury car is the rule that we are checking, and again 204 says that horsepower greater than equal to 8 is 800, which is greater than equal to 700, right? So this precondition is satisfied. This is fine. This says that the tire is regular, which is also satisfied, right? And then 210 says that the passenger limit is 2, which is also satisfied. So here we see that all the preconditions for luxury car are satisfied. Okay, so luxury car will be a part of the conflict set. Okay, yeah, thanks Vanshika. Yeah, you are right. Option B will be a part of the conflict set. Let's look at the third option, which is regular car, and that takes in as inputs the elements 203, 6 and 9. So let me just erase this first. All right, so we are checking regular car, okay, and we have working memory element 203, which says that the horsepower is 280. So 280 is in fact between 100 and 300, right? So these two preconditions are also satisfied. Next is 206, which says that the tire is regular. This is also satisfied. The tire is regular. Okay, and then 209, which says that the passenger limit is 4. This is also satisfied, right? So even for regular car, all the preconditions are satisfied. So regular car will also be a part of the conflict set. Okay, so now as of now, we have two rules in the conflict set. Let's look at the other option. The other option is minivan with rules with elements 202 and 208. Okay, so let me just erase this. All right, so we are checking minivan now with rule 2 with element 202, which says that horsepower is 290. Okay, so horsepower has to be less than 300, which is 290 is less than 300. So again, this precondition is satisfied, right? And then the other one was 208, which says that the limit is 8. Okay, and also this is also satisfied for minivan, right? Which is horsepower is greater than 100, and the limit is also 8. So that is also satisfied. So this will also be part of the conflict set. Now we had one more option with minivan. Okay, let's quickly check that, which is minivan with elements 203 and 9. So we are checking minivan again. 203, horsepower of 280, which again does satisfy these preconditions. And the other element was 209. But this says that the limit is 4, right? But minivan needs to have a limit of 8. So this precondition is not satisfied. So this instance of the minivan rule will not be part of the conflict set. Okay. So the three options that will be part of the conflict set would be luxury car, regular car, and minivan with these particular elements. Okay. Any doubts about this question? Yeah, Orgodeep, you had raised a hand. Okay. Thanks for the thumbs up, Orgodeep and Somil. All right. So again, this is one of the easier questions. Let's now move on to the 11th question, which asks, in the retinet, find the locations, the alpha nodes, where token 204 resides. Okay. So let's again shift back to our retinet. So we are being asked about token 204, which is this one. And we have to find out the alpha nodes where this is residing. Okay. So what information does this tell you? 204 tells you that the power of this vehicle K32 is having horsepower 800. Okay. So just look at the alpha nodes and tell me which are the alpha nodes where this condition is satisfied. 800 is greater than equal to 700, right? So this is one alpha node where this could reside. Is there any other alpha node where it could reside? No, Vanshika, tell only the lowermost alpha node. Okay. So if you talk about A6, A6 is not checking the condition for horsepower, right? A12 is. So don't include A6 in the answer. So among A12, A14 and A15, is there any other node? Yeah, it's A14, right? So this is also satisfied, right? So one of the answers you said was correct, and the other answer you said was also the other answers. Some of you said A14 was correct. So the two alpha nodes where this would reside is A12 and A14. Okay, I hope that was clear. Any doubts about this question? All right, great. So now let's move on to the 12th question. So now we come across another type of conflict resolution strategy, which is specificity. Okay. So we already saw that the three rules in the conflict set were luxury car, regular car, and minivan. Okay, so this B, C, and D. Now, if we have to select which of these rules to fire based on the strategy of specificity, which rule will we fire? Okay, so if you remember, specificity tells us fire the rule that is the most specific, right? And when you say most specific, you mean that which requires the testing of the largest number of conditions to match the prerequisites or the preconditions for that particular rule. Okay. Okay. So, Vanshika, you are suggesting two rules. Uh, so the aim of the conflict resolution strategy is to come up with only one rule to fire. So if you have to further narrow down your answers, if you have to select only one answer, one rule that you could fire, then which one would you select? B. Okay. So let's see uh, whether B is the correct answer or not. So one way you could do this is to calculate the sum of the path length, okay, that you need to have in order to check the preconditions. Okay, so when I say that check the sum of path lengths, let me just zoom it a bit. All right, so for option B, which was luxury car, okay, the conditions that we were checking were tire is regular, okay, so this covers three edges, this one, and this one, okay, so we have 3 plus another 3 in the form of this, and then we have another 3 edges, sorry about that, in the form of this. Okay, so you have 3 plus 3 plus 3, which is basically, okay, sorry about that, 9. Okay, for luxury car. Now let's check it for regular car. For regular car, how many edges do you have to check? 1, 2, 3. Okay, so you have 3 plus 1, 2, 3. 1, 2, 3. Sorry about that. 1, 2, 3, which is 12. Now let's check the other option, that was minivan. Okay, for this you have to check 1, 2, 3. So 3 plus 1, 2, 3, and 1, 2, 3, which is 9. So the most number of uh, edges is turning out to be 12, which is in the case of regular car, which makes sense, right? Because if you think about the preconditions for regular car, you are having to check these 2 horsepower conditions. One is that it is greater than equal to 100, and one is it is less than equal to 300. Whereas for the other rules, that is for minivan and luxury car, you are only having to check one condition for horsepower, right? So regular car is more specific in the sense that you are having to check more things to see whether the prerequisites match, right? So regular car is more specific. Hence, the correct option would be option C. Okay. Any doubts about this question? All right, that's great. So now let's move on to the last question, which is yet another conflict resolution strategy, which is recency. Okay, so again we have the same elements in the conflict set, which is luxury car, regular car, and minivan. Now what recency tells you is that you should fire that rule from the conflict set that contains the working memory elements that are most recent or that have the uh, higher time steps. Okay, so if I have to give you like a summary of the recency test, it will be something like this. Okay, so I'll just read it out for you. In a conflict set, for two conflicting instances of same or different rules, recency is decided by listing the working memory elements in descending time sequence and comparing the ordered list and selecting the dominant one. Okay. For example, if you had something like this in the conflict set, so you had one rule 7 and rule 2, you arrange the working memory elements in descending order. Okay, so see 210, 208 and 207. So this is arranged in descending order. Similarly, do that for the other rules as well. And then you arrange all these rules again in descending order, right? So see, rule 1 has 210 first, so it is on the top. And rule 7 also has 210 in the first, but then in the second case it has rule 200, it has 202, not rule, element, sorry. And rule 1 has 208 element over here in the second position. So rule 1 occupies the first position, rule 7 occupies the second position, and rule 2 occupies the third position. Based on this, you select that you fire rule 1. Okay. So is the definition of recency clear? Is the concept behind recency? Any doubts about that? All right. So let's go back to the options. Uh, so Vanshika, option E can't be correct because remember E is not even a part of the conflict set, right? So when you are using a conflict resolution strategy, you can only choose among the rules that are a part of the conflict set, right? And we already saw that the rules that are part of the conflict set are B, C, and D, right? So you have to select from among those the one that is the most recent. And if you do arrange them in the way that we just discussed, you will have something like this, right? So luxury car will be at the top, followed by regular car and then minivan, because this has the most recent element, which is 210. This one has 209, this one has 208, right? So you will select luxury car to fire, right? So the correct option would be option B. Okay. Any doubts about this question? All right, that's great if there are no doubts. So that brings us to an end of the questions that we were to discuss today. Before I go, there was one doubt that was raised in the previous live session by Mr. Kamlakar. So is he here? Is Mr. Kamlakar here? Okay, I guess he couldn't make it to the session. I'll just verify it. Okay, that's fine. So I've also posted this trace and this question that he had asked in the discussion forum. So you can also refer to that. So you will have this available to you. So basically what he wanted to know is why was this, so this was the scenario that was given, and he wanted to know why is this evaluating to false. Okay, and the reason is that it is evaluating to false because this likes Abby comma O, that is evaluating to false. And the reason behind that is when we make a query called likes AB comma 0 comma O, it follows this particular definition. Okay, so first it checks whether orange O is satisfied, and it is satisfied because it is part of the knowledge base. And since this is true, this cut operator moves the control to this part of the definition, and it restricts the evaluation to this part, right? So it forces it to fail, as a result of which we get a false output over here. And since this likes Abby 0, Abby comma O evaluates to false, this whole thing evaluates to false because this is like an AND, right? And so even if this evaluates to true, since this evaluates to false, the final answer is a false. All right, so this was just the doubt. And all right, so I think there was another doubt regarding some error that was occurring when one of your colleagues were trying to use Prolog, which was goal could not be found. uh, I think that has something to do with the syntax. Okay, so just make sure whoever was I'm sorry, I don't remember the name of the person who had asked that question. Whoever had asked it, just make sure you are following the correct syntax, and hopefully that shouldn't be an issue later on. All right, so let me see. All right. So today I have to rush to another meeting immediately after this. So are there any some quick doubts that we could discuss right now? Else we'll end the meeting over here.
No, sir. You can just close this one.
Okay. Thanks, Mohan.
Thank you.
So
Thank you so much.
yeah. So we'll end the session for today. And thanks, Soman. Thanks, Naresh. Thanks all for attending the session. And let's meet next week.